Imagine you're a transformer model learning to predict the next token in some corpus of text. As you read each token, there are a lot of things you have to keep track of. People, places, writing styles, grammatical constructs. And all that information needs to be encoded in a giant vector called a residual stream. This vector is the only thing that gets passed from one layer to the next. So at the last layer, when it's time to predict the next token, the residual stream should contain all the information you need to make that prediction, somehow encoded as floating point numbers. Maybe one way this could work is you could assign each dimension of the residual stream to a different feature of the text. Like, the next line should rhyme with this one. Or, I think this is Python code. And then you'd have a numerical value there that says to what extent the feature is present. For concreteness, let's say this is a Llama 3 model with 8 billion parameters. So the residual stream has 4,096 dimensions. With one dimension per feature, you could encode 4,096 different features. The problem is that isn't very much, at least compared to the set of all possible features that a string of text might have. To do well on benchmarks, or even have a simple conversation, you'll probably have to pack a lot more information into the residual stream. So, how? This is a phenomenon called superposition. It's a little mind-bending to think about how superposition works in a real LLM, so let's simplify things. Say somebody just hands us a vector where each dimension is a different feature to encode. It doesn't matter exactly what the features are, but we can guess that this vector is going to be mostly zeros. If you think about how language works, most tokens are not part of a rhyme. Most tokens are not Python code. Most tokens are not names of cities. Most things just aren't most other things. We need to be able to represent any of these features, and many others, but we only need to be able to represent a few of them at a time. So in our toy model, we could say that this is a sparse vector, where each feature is only active with some probability p. If it's active, then it's a random number between 0 and 1, and if it's inactive, then it's just 0. The sparsity thing will be important later. Okay, so we get these features as a sparse vector of some size, say n sparse, and we want to encode the features in a small, dense vector of size n dense. We'll say we succeeded if we can reconstruct the original feature vector with a small mean squared error. Because this is a neural network, we want to do the encoding with a single matrix multiplication, and then the decoding step will be another matrix multiplication, plus a bias, and an activation function, like ReLU. What we've set up here is an autoencoder. All we're trying to do is make the output as close as possible to the input. Another way of saying that is we want to find a pair of weight matrices so that WOUT times WIN is pretty close to the identity matrix. Or really, it can be the identity matrix plus or minus a constant, and also it's fine if we end up with some negative numbers where there should be zeros, because the ReLU will take care of that. Let's start with the easy case. If n dense is equal to n sparse, then we can set WIN to the identity matrix, set WOUT to the identity matrix, and then, ta-da, identity times identity is identity, and we get 0 reconstruction error. But as the dense vector gets smaller, the weight matrices are going to shrink along these axes. And WOUT times WIN is going to be the same size, but it's going to be low rank. And an identity matrix isn't low rank. We could just delete some rows and columns from these weight matrices. That would correspond to the one dimension per feature approach. And we'd get perfect reconstruction on the features we keep, but the others would be lost entirely. What if we chose weight matrices that somehow spread out information so that features don't rely too much on any one dimension of the dense vector. Then, if we have to delete some of those dimensions, we mess up the reconstruction of many features, but we only mess them up a little bit. And that's actually better, because if the error is small, we can mostly recover from it. We want to make sure this product matrix still has high values along the diagonal, so we'll keep W out equal to the transpose of W in. That way, each of these diagonal entries is basically the dot product of the vector with itself. And we still want zeros off the diagonal, so we need to make sure that the ith column of W in is orthogonal to every row of W out, except for the ith row. Or equivalently, the ith column of W in is orthogonal to every other column of W in, except for the ith column. But this time, we don't want to do that by setting all of these entries to 0. We want to spread information out. So concretely, all of these entries should have the same absolute value, but if you take this column and another column, the signs should match in exactly half the rows, and mismatch in the other half. And so let's say that absolute value is k, then the dot product of these two columns is some number of plus k squareds, and this same number of minus k squareds, and it all cancels out. Can we create a matrix like this? Well, if we only have two columns to worry about, then it's really easy. On the top, we'll put plus k, and on the bottom, we'll put plus k minus k. Every entry has the same absolute value, and every column has a positive dot product with itself, and 0 dot product with the other. What about a bigger matrix, say 4 by 4? We can actually use a similar pattern, but instead of a scalar k, we'll work with 2 by 2 blocks of the matrix. We just have to make sure that the signs are the same on top and different on the bottom. We also have to make sure that within one of these blocks, the half columns are orthogonal to each other. But that's the problem we just solved. So we can take this matrix and make 2 positive copies of it, and then a positive copy and a negative copy. And if we want a bigger matrix, we can repeat this as many times as we want. Oh, so what's k? The dot product of one of these columns with itself is going to be n dense times k squared. So if we want that to be 1, then k has to be 1 over root n dense. And there we go. If we multiply this by its transpose, we get the identity matrix again. But now, every time we delete a row of W in and a column of W out, the entries in the product matrix only change by plus or minus 1 over n dense. So we don't lose any of the features entirely. We just get some noise off the diagonal. As for the diagonal entries themselves, we can just rescale everything so that they're still 1. Let's take a closer look at that noise. So each of these off-diagonal entries is a sum, and when n dense equals n sparse, half the terms are positive and half the terms are negative. They might come in any order, but they'll always add up to 0. When n dense is smaller than n sparse, we're sampling a random subset of those terms. Technically, this is sampling without replacement, but if n dense is small enough, we can pretend the terms are independent and say each one has a 50% chance of being plus 1 over n dense and a 50% chance of being minus 1 over n dense. As we add more of these terms together, we get something that looks closer and closer to a normal distribution. So, in any given column of our matrix, the noise might look like this. It's pretty small compared to the diagonal entry, which is the feature we're trying to encode. But if we have multiple features active, then the noise from those columns is going to get added together. And if we're unlucky, or if someone's intentionally trying to mess with our model, that could be pretty bad. Here, we were only trying to encode features 1, 3, 5, 8, 10, and 12. But in the reconstruction, it would look like these features are active too. This is why it's important that the feature vector is sparse. As long as we're only adding a few of these columns together at a time, the signal will probably stand out from the noise. But even if we can see the signal, mean squared error is still going to penalize all the noise. And by that measure, we're actually worse off than we were with one dimension per feature. But here's where the bias and the ReLU come into play. We can use them to essentially set a threshold and filter out any noise below it. Now, there might be some signal below this threshold. Remember, we said active features can be any random number between 0 and 1. But it turns out this is a trade-off worth making. You could think of this like a least squares regression, where the y values are the features we'd ideally like to reconstruct, mostly zeros, a few of them active, and the x values are y plus some noise. If we just use the identity function, our mean squared error would look like this. Not very good. The actual line of best fit would look like this. We're getting a few large errors on the active features, but they're balanced out by a lot of small errors on the inactive features. This is about as good as one dimension per feature. Now watch what happens when we do this regression with a ReLU function. Here, we're kind of getting the best of both worlds. Most of the noise is eliminated, and we're only distorting the signal a little bit. The coefficients for this regression are going to depend on a couple things. If the input vectors have very few active features, then it makes sense to set a somewhat large negative bias and compensate with a larger scaling factor, because we know most of the features are supposed to be 0. Inversely, if there are more active features, then both the bias and the scaling factor should be smaller, because we have no idea where all these points were supposed to go. How about n-dense? If it's high, then the x values are already pretty accurate, and there isn't much to do. If n-dense is too low, then the x values are really noisy, and reconstruction is kinda hopeless. So the best we can do is guess a low y value for everything. It's the intermediate values of n-dense where the threshold thing really provides an advantage. Okay, so to recap, we have these two square weight matrices that multiply together to give us the identity matrix. When n-dense is smaller than n-sparse, we lose rows and columns from our weight matrices, and this product becomes a noisy low-rank approximation of the identity. If multiple features are active at the same time, the noise from the corresponding columns gets added together. But we can at least partially filter it out by applying an extra scaling factor, and a bias, and a ReLU. The scaling factor can be folded into our weight matrices, so this matches the form we were looking for. Whatever n-dense is, the loss with these weights is going to be at least as good as it was with one dimension per feature. Often it's much better. And it's about the same as what you get when you train the architecture using gradient and descent. The representations in a real LLM are no doubt much more complicated than anything here, but toy models can at least give us some hints as to how they might work. This video was based on a recent paper called The Persian Rug: Solving Toy Models of Superposition Using Large-Scale Symmetries. If you want to learn more, I'd recommend checking that out, as well as this earlier paper that introduces the toy model. You can find links to both of them in the video description.